What we're going to give you today is really probably the overview of things you can go out and explore on the systems that we're going to tell you about. One of the systems that I'll talk more about is Keeneland, and that's an NSF system. That system's relatively open. People from across the country can use it for production science. They can also use it for education and tutorials and things like we're going to do today. I wanted to put these slides up first. I know several of you have already logged into Keeneland. With the time we have, what I'd like to do is use the breaks to come around and diagnose any problems you might have logging into the system. We do have a lot of material online at this website. You can go to the Keeneland Kids Quick Start, and that has a lot of the material that can help you log in, configure your environment. It looks very much just like an MPI cluster. So you can log in and just use it to run regular MPI jobs. It has a Moab and Torch scheduling system that you have to use to submit your jobs. There are sample scripts and other things on this page for that as well. The one keyword that's not on the web page is just for your tutorial, and that's the allocation for the accounts that you have. The tokens they've handed out are tied to this particular account allocation, and so when you run your PBS script, you have to plug that in where it says what account to charge your time to. And this is in the slides that are online. The other thing I'd like to mention for your time experimenting is there's a lot of code out there. So I'm sure you've seen NVIDIA and some of the other sites that have a lot of examples. One thing that we've developed over the past few years is a benchmark suite called the Scalable Heterogeneous Computing Benchmark Suite. And it's nice because we have many of our tests implemented in MPI, OpenCL, and CUDA, and we've actually got a mic version from Intel that's been posted there as well. So if you're interested in seeing how these programs are written, how you combine MPI and OpenCL, for example, you can go there and look at them and see what the code looks like to do a fast Fourier transform or molecular dynamics or something like that. And that's downloadable from the GitHub site that you see right there. And we've run it on many different platforms. Keeneland's a platform it runs on all the time, so it will run there. So with some of the logistics out of the way, let's start talking about heterogeneous computing. If you look at where we are today in emerging computing architectures, it's quite a different landscape than it has been over the past 2 decades. And what I mean by that is we're seeing a lot of interesting features emerge in the commodity computing market. If you just look at the Ivy Bridge chip from Intel lately, which some of you probably have in your laptops, it has a GPU on board that you can program with OpenCL. You can take that and the OpenCL techniques that you'll learn about here and actually program that device and use it to do some accelerated image processing or floating point computation. That's something that I believe we're going to see a lot more of over the next 10 years. It's just a matter of the technology trends that we see in microprocessor design. Another interesting one that I'm not going to talk about today is really this idea of new memory devices, and this is another project we have, but I wanted to bring it up because it's really interesting, and it's also driven by the commodity marketplace. That is a switch away from DRAM memory technology to non-volatile memory technologies. And the reason for that's really not performance per se, it's for power and capacity. And so you've seen these flash sticks that you can buy, the camera cards that you can buy that are, I don't know, 32, 64 gigabytes for $20, right? They don't need any power when you're not using them. They really only need power when you're accessing them. And that same idea we expect to be used in a supercomputer in 5 to 10 years. And so one of the things we're doing is looking at applications in the software stack to figure out how that would be integrated into a future exascale system. And then there are other things I'm not going to talk about here, but I think the key takeaway message is really it's a dynamic environment right now, and that has implications on the things you need to learn. If you just look at the latest system announced last month, it's a large heterogeneous system. It uses the Xeon Phis. Everything else looks pretty much like a large-scale system. It's got similar interconnects, it's got similar I/O storage system, cooling, racks, everything looks pretty much the same, except it has that heterogeneous node. And you have to understand how to program it and optimize it in order to make full use of it. And then Titan, which we've talked about and some of you have access to. It's an NVIDIA-based system using the K20X GPU, and it has, on the order of magnitude more floating point capability in the GPU than it has on the node itself. And so this, to me, this is getting really interesting. Right now we're looking at these as separate devices, but as I mentioned with Ivy Bridge, we're seeing more and more of that come on chip, and that's going to continue for the next few years. And here's just a simple chart of what we've been seeing in contemporary HPC. I mean, just over the past 3 to 4 years, there's been a really large change. You have some systems that are homogeneous, like the Jaguar system that Titan replaced at Oak Ridge. You've got K, which is a homogeneous system, but you see a lot of combinations up here. And again, we expect that to continue, at least for the foreseeable future. And a lot of that has to do with power. And I know you had some presentations earlier in the week, so I'm not going to dive down into the details there, but one of the big constraints is just power and how much power you can bring into a building to manage the system. So just one point that I want to make about the fusing of these architectures is we've used shock, and this is just an example of the complexity of architectures that we're starting to see. When you have something like Ivy Bridge or this AMD Llano chip, basically, instead of having two discrete devices, having your node CPU and memory and your GPU and memory, and having to cross the PCI Express bus to transfer data and control the GPU, it's all really in one socket, one package. And so even the memory systems are combined. It doesn't necessarily mean you can load and store to those memory locations from either device, but it makes it much, much faster and much lower latency to be able to transfer that data. And that's an x86 core, just like the AMD x86. You've got 4 of them, and then you've got a whole group of GPU cores, and it looks like a GPU for the most part. It's typically fewer cores than you would have on a discrete GPU. But the big key is you don't have that multi-microsecond bump that you have to transfer data across the PCI Express bus. And what we're trying to point out with this chart here, and I don't want to belabor it, but basically this is the timing of our kernels not counting the data transfer cost, and this is the timing of the kernels counting the data transfer cost. And what we did here was compare that onboard GPU to 2 discrete GPUs from AMD that plug into the PCI Express slot. And so basically what this shows you is the discrete GPU does really well if you have the data on the GPU and you can leave it there. It beats the local GPUs, on-chip GPUs, almost every time. When you take away the PCI Express bus, it gets a lot more competitive, even though that's a smaller and slower GPU on board. And so this is the way it's changing, and this was what makes some of the software and performance tuning a lot more complex. Memory bandwidth that we observed from the unified North Bridge compared to PCI Express.
Right, on that chip.
On that chip. And I think if I remember correctly, it's in the paper, if I remember correctly, it was on the order of 25 gigabytes per second for the memory bandwidth. And it's not using GDDR memory, it's using your normal DDR3 memory. And so you lose something there, and that's another consideration that you have to think about. But that latency and that bandwidth that you have for PCI Express is like 5 gigabytes per second and microseconds on orders of latency. So I threw this out, future directions in heterogeneous computing. I think we're going to see a lot more of this, many core. You might have 3 or 4 different kinds of cores on a chip. You might have one there to do something like a different type of image processing or AES processing or something like that. Plus you have all these things like transactional memory and random number generators, and scatter-gather. All that stuff is coming, and we need to be able to understand how to take these features and integrate them into our code. Just to give you a target, when we were working with NVIDIA a year ago, we came up with this system sketch of a system called Echelon, and this was an idea for an exascale system. And this was, if you look at the lowest level of the nodes, basically a processor chip would look like this. It has a lot of streaming multiprocessors, a la Fermi or Kepler, and it's got some latency optimized cores, x86 type of cores, or ARM. And then you've got some L2 cache and a memory controller and a network interface. And that memory controller goes out to some stacked RAM cubes and non-volatile memory that we can have. And that can be used for resiliency or big lookup tables or a lot of different features. Then you take that and put several of them on a board and then a cabinet and scale it up with something like a Dragonfly interconnect, and you have yourself an exascale system in about 400 or 500 cabinets, which is slightly more than we have now, but it's something that you could actually see being built rather than, thousands of cabinets. So just to finish up here, this has a lot of implications about what we're talking about today. If you scroll back 10 years and look at the landscape of computing, it was MPI, C Fortran, maybe OpenMP. That was pretty much it. It's changing very rapidly. You've got the Mike programming interface, you've got OpenCL, you've got CUDA, you've got other compiler interfaces coming on the market. If you're writing a code, which one of those are you going to choose? If you have $1 million and you want to start writing a new code, it's hard to tell. You really have to place your bets. It's a lot riskier than it used to be. So, got a lot of implications for us. The functional portability, you can't, that's something you have to worry about right off the bat. Performance portability is the other challenge with something like OpenCL. It runs everywhere. There are FPGA versions of OpenCL now, where you can actually take the code you write in an OpenCL and run it on an FPGA. And that's really, incredible. The problem is there's a lot of performance portability issues there, and you have to have some way to tune that. There's a lot of fast-moving research standards products. I put this up here just a couple days ago. NVIDIA bought PGI, right? One of the reasons for that is they see this complexity and some of the challenges with CUDA, and they want some compiler experts to come in and provide tools like OpenACC to make it easier for people to start using GPUs and heterogeneous processing. And just as a matter of point of fact, I wanted to put this slide up, the directive-based GPU programming models, and Bronson's going to talk about that some later. We've got our own set of benchmarks we use there. We've got them written in CUDA. We have them different compilers. Here's a sampling of them. There's a PGI Accelerator, an HMPP, and OpenACC. And Blackline is handwritten CUDA. And basically what you see is with some of the benchmarks, compilers are starting to get reasonably competitive with handwritten CUDA. There are a couple outliers, and we understand why there are outliers. If you look at many of those compiler models, they don't allow you to control things like the shared memory very well. And so for this particular LUD example here, it's very good in handwritten CUDA because they do some very intricate tiling of data into that shared memory. And it's hard for a compiler to do that given the current state of compilers that we have. But it's fast moving. There's a lot of investments right now in compilers for this. So that was my motivation in a nutshell. Any questions? Does anybody believe that heterogeneous computing is in their future? Raise your hand. Come on. Okay. So, and this is also driven by the mobile market and other markets. OpenCL runs on almost every mobile platform you can get out there right now. Someone downloaded our Shock Benchmark suite and actually ported it to Android. So that if you go out to GitHub, you can find an Android port of our Shock Benchmarks. It runs on ARM with Mali GPU. Mali is ARM's GPU. And so with that background and motivation, I'm going to move on and just start talking about a specific example. So Keeneland is an NSF project. You guys have already logged into part of that system. It is a system that, it's an HP cluster. It's got 2 Sandy Bridge sockets in it with 8 cores per Sandy Bridge. Then it has these risers. Those risers connect to GPUs, and so that's through PCI Express. And basically, we have 3 Fermis in there right now. We're hoping to upgrade to Kepler in the near future. That'll depend on how budgets work out and all that fun stuff. But this is what the node architecture looks like for that. You take 264 of these and put them together. It turns out to be about 13 racks, and connect them together with an FDR InfiniBand interconnect, and you've got yourself 615 teraflops in that small floor space. So just to look down at the architecture in a more logical format from a programming perspective, this is the architecture you're going to be working on. This is the kids architecture, which is slightly different from the architecture that I mentioned earlier. It has 2 Westmeres, but close enough to CPUs, Sandy Bridge. Then they have their own local memory. Then they have these I/O hubs that connect to the GPUs the same way that the earlier system did. You need to do several things here. Just looking at this diagram, you have to control your communication over InfiniBand through MPI. You need to worry about NUMA. You've got a bunch of cores here on these chips that you can use for computation and management. And then you've got these 3 GPUs over here that you have to control and transfer data to. And so just that in and of itself turns out to be reasonably challenging thing to do. If you look at the Fermi, and I'll be talking about CUDA, I put a introduction to CUDA in here, so we're going to go through this in reasonable detail later. But if you just look at the high-level view of the Fermi chip that you'll be using, it's got 512 CUDA cores, and that's these cores right here. They're very simple cores. They don't have nearly as much functionality as a CPU core in terms of caches and branch prediction and pipelining and all of those things. They're much simpler. The benefit to that is they're smaller and they use less power. And given that, you can put a lot more of them in the same die space that you would something like a Sandy Bridge. And they do floating point. It wasn't 5 years ago where almost none of these GPUs did IEEE floating point. You know, you had some graphics optimized floating point that they would do. Now they're doing what we do on our CPUs. Depends on what SKU you get for the GPU, but this has 32 cores per streaming multiprocessor, and that's just a terminology for a small, it's like a small SMP within the GPU that collects the cores together and shares memory. And then it has that great GDDR, which we already talked about. One of the big benefits, kind of the unsung heroes of GPUs, is the fact you've got this GDDR, which is graphics memory. It hits about 178 gigabytes per second. And when you look at some of the latest CPUs, the memory bandwidth you're talking about is on the order of 25 to 50, depending on which CPU you're looking at. And so that's huge compared to CPUs. And then you got the other stuff, the floating point rate everyone knows is pretty high. The other key is, for the longest time, GPUs didn't have ECC anywhere. I mean, think about it. If you're building a graphics card for your gaming and you have to reboot, no big deal. But if you put 18,000 of these in one large system and you have some probability you're going to have to reboot them occasionally, that's probably all you're going to do. And so they've added ECC to almost all of the components on GPUs today. And that's configurable. One of the interesting things we've been doing is running some of our applications with ECC on and ECC off, because you can turn it on and off with firmware, just to see how much faster it is. In some cases, the applications actually run faster, and we're trying to understand if there are some apps we can run all out without ECC and know that there's an error if there's an error in the execution. And you get higher throughput that way. So I'm just leaving this chart in here. This shows you some differences in the system you'll be on and then the full-scale system. The general idea when you're starting programming, and we'll start diving into CUDA in the next few minutes, you have to think about it as two different devices. You've got your CPU and your GPU. GPU's got hundreds of these small cores. Something like Kepler has on the order 2,400 of these cores. So that's a huge number. If you look at starting to aggregate all of those ideas and concepts together, you have to use a mix of programming models to build a scalable application these days. There's not one paradigm that you can pick up and say, I want to program all of these devices, distributed memory, shared memory, CPU, and GPU, and have it be in one language, one nomenclature, one programming model. You have to use different programming models. And so this is where I put this chart together to give you an idea of what people are doing today to program these different devices. Now, if you look, everyone's still using MPI across the system. So whenever you have multiple nodes and they have to talk to one another in a distributed memory fashion, everyone's using MPI for that. And you have to worry about things like keeping the overhead low and resource contention in the network and locality, having the data where you need it. And then you heard OpenMP talks yesterday, where you have something like OpenMP or pthreads on the shared memory node. And that would be, once you got down to this node, you would have to start worrying about things like, am I SIMD-izing my code and loops well? Do I have NUMA under control? We've seen instances where we can change the performance of the application by tweaking the NUMA, the data layout, that gives us maybe a 30% boost in performance. And that's just using the SMP and MPI. And so that's a real challenge. And what we're going to talk about now is this lower level where you have to reach out and start programming the GPUs. And you can use something like the compilers. Brunson's going to tell us about OpenACC, CUDA, or OpenCL to reach out and do that. Now, it's got its own set of performance challenges. Those include things like being able to access your memory properly. And you can see an order 10x difference if you don't access memory properly on a GPU. And so that's very important. There's the whole data orchestration. You're sending data back and forth between the CPU memory and the GPU and perhaps over InfiniBand. You know, how do you do that so you overlap computation and multiple types of communication at the same time? That's really tricky. Then there's the fine-grained parallelism. That is where you actually have to have these threads in a GPU are much smaller than a thread you would have in OpenMP. And you can actually have a hardware thread in a GPU do something like calculate 20 or 100 flops. And that would be why you'd create the thread. And it would be created, scheduled, do its work, and die just to calculate, you know, a few dozen flops perhaps. And then finally, there are hardware features, and I'll talk about some of those. There are things like atomics that you can use to help, you know, get correct code, but you really need to be aware of when to use them and when not to use them because they can impact your performance. Just to talk about software briefly, if you look at the software environment on Keeneland, we have, you know, it's integrated with NSF Exceed, so it looks very much like any other NSF system that you might be working on. And then we have these extra programming environments. We have CUDA, we have OpenCL, we have compilers that are enabled with GPU like OpenACC or PGI Accelerate. And then we've got debuggers, performance tools, and some accelerated libraries. If you have a code that does big matrix multiplies or FFTs, you don't have to even write CUDA. There's libraries out there that you can just link to that will use the GPU and hide it from you and go out and execute your FFTs and matrix multiplies and other things on the GPU for you. We don't have enough time today to cover all this. I mean, I'm going to talk about CUDA and give you a whirlwind tour of that, but you can find information about these online. So that was, again, a very brief introduction to Keeneland. That's a platform we have on the floor today. That's what we're going to be talking about specifically. So, I mean, have any of you programmed the GPU before? Oh, you're not allowed to ask me hard questions, okay? I've been doing this for a while, but there's always something new that I don't quite know yet. So anyway, this is a basic introduction. We don't talk about some of the advanced features like hyperQ or dynamic parallelism yet. That's something that after you get the basics down, you can go explore. So let's start off with, you know, what is CUDA? You know, it's basically, if you scroll back and think about GPU computing about 5 years ago before CUDA, it was horrible. Early GPUs did not have branch instructions. You had to access memory in very specific ways or your kernels would die. You had to load the kernels through OpenGL and try and stand on your head to get that stuff to work. CUDA was really incredible in the sense that people started using it as rapidly as they did. And so it looks like very much standard C. There's some extensions to it that you have to understand in order to be able to use it. And then there are some APIs that you need to be able to use to access the device, be able to transfer data back and forth in memory. And then we'll talk about things like optimizing some of those features. So basically, this is an outline of what we're going to do. We're going to start with the very high level and just walk through a simple write and launch of a CUDA-C kernel. We'll talk about the memory, we'll run some parallel kernels, and then talk about communication and synchronization, and then some warnings about race conditions and how you might be able to use an atomic operation to fix that. So the basics. So if you saw my earlier slides, there's some terminology we have to have. The host is basically the CPU and its memory, and that's typically a node, a motherboard, you know, with an Intel or AMD chip on it, plus some memory. Then you've got the device, and in CUDA terminology, that always means some kind of GPU that actually runs the CUDA code. Of course, you know, you can take a standard program and just run it there and compile it with NVCC, and it doesn't complain. It says, you know, this is just standard C, so I'm going to generate some host code for that, and you'll be able to just run it. And that's, you know, pretty much the simplest thing you can think of. Now, What you really want to do, of course, is use the GPU. And so you have to learn how do you invoke that. And this is a kernel, and we'll explain the details of this as we walk through more examples. But basically, you create a kernel, and this kernel looks something like this. It has some decorations on it that make it noticeable to NVCC. And then when you are in your main host code, you basically can run it by invoking it this way. And basically, it's just some overloaded operators, your kernel, and then I'll tell you what these numbers mean in a moment. But that's normally the way you would run it. And then the hello world would, be printed out by the host. So the key thing you have to think about here is how you're managing the interactions between the two. The NVCC compiler builds this single executable for you, so you don't have to worry about multiple codes and linking them together and manage them. I mean, if you get more exotic, you might have to do that, but basically, you could type this in and run it now and have it compile correctly with NVCC. So what does all this mean? So if you look at the CUDA keyword _global, it really means this is meant to run on the device. And again, device means the GPU, and it's called from the host. Now note that sounds simple, but there's also routines you can have that are called from the device itself. So if you have code that you want to run on the device and it's called from the device, you have a different one for that. NVCC automatically takes care of splitting these two things apart, and the compiler handles a lot of this heavy lifting for you. And then the back-end compiler can be GCC, Intel, Microsoft, whatever you want on the back end. And we talked a little bit about this. If you look at that kernel code, basically those angled brackets you see up there is what's called a kernel launch, and that's where you're actually executing. We don't transfer any data yet. That's coming. But that's the way you launch a kernel. And if we have parameters, they would just be in that bracket like a normal function call. So just take a more complex example and start walking through this. So now we want to start doing something interesting, like adding two integers together. And so here's a very simple routine that we're going to do that. We have global, because we're going to be calling it from the host to the device. No return value. We're going to add, that's a function name, and then you got your pointers. And notice these are pointers here, because what we're going to do is make those vectors in the next few minutes. But these pointers are also to things in device memory. So you have to allocate memory for that. Global is that keyword, and it means that it will execute on the device and it will be called from the host. And again, this is primarily what people will be writing when they're writing a CUDA program. We'll use pointers. Like I said, the A, B, and C must point to device memory. And then the next obvious question is, how do you allocate that memory? And remember, we've got two different memories here, so you have to allocate in both places and then copy data back and forth. So these device pointers point to GPU memory, and you still have to manage them on the host side. So you get a handle back, and that handle really is represented by that pointer. Then when you pass that handle in to some of your functions or your routines, the routines are smart enough to take those and translate them into something that's local to the device. And you can't really use those from the host code, so you can't take that A that I was talking about earlier and access it and start touching memory. It would cause typically a seg fault. So the basic CUDA API for dealing with device memory is very similar to what you use in heap memory in a regular code. So there's malloc, there's free, and there's memcopy. And the memcopy works both ways. So if you're sending data to the GPU or taking data away from the GPU, that's what you use. So if we go back and take a look at main for this particular kernel that we're working on, it would look something like this. So here's your main, there's your host copies of A, B, and C, and remember we're just doing a scalar right now. Then we want to have a pointer to the copies of the data we're going to have over there. So we're going to have two copies. That's where the inconsistency issue can come in. And then we just create a size, so we know we're going to have to use that later. We have to allocate device copies of A, B, and C. Remember, we automatically allocated that up here on the stack. If you go to CUDA malloc, and you have to get the handles to it, and you have to allocate it. And that's what you're doing right here with those malloc routines. And then we're initializing the variables on the host side. Once they're initialized, we're going to copy them over. And remember, it's the CUDA memcopy. You're copying it from local to remote, and there's the size. And this is just a parameter that tells you whether you're going one way or the other to the host. You've got the data over there. You've got your memory allocated. You've got the handles to it. Now you can invoke this add kernel that we talked about with those parameters. And this is the simple way you do it. Okay, you've got your add routine. You've got 1, 1. And I'll tell you about 1, 1 in a moment, so hang in there. And then these are the parameters for accessing the 2 input vectors and the output vector right there. When you're done, you need to be sure to copy it back, and that's what you use this routine for. And you see that parameter's changed. And then finally, you free memory. And we allocated memory on the device, and this is a memory leak, so you have to think about managing your memory on the device the same way you do on the host. If you keep doing mallocs and don't free, you're going to run out of memory at some point on the device. And sometimes GPUs don't degrade gracefully. They don't have a lot of operating system code or control code on them, and you can get some unintelligible errors if you're not careful. So that's really the kernel, and now we're going to start talking about how you can do parallel. So I mean, if you had 3 additional parameters in addition to those I had up there, so good question. How would you handle global variables or other types? So the global variable in a C-scope, your main, would still be just a host-side allocation. You'd have to allocate a copy of that on the device side and pass it over there the same way. So they're 2 distinct pieces of memory, and so you'd have to manually do that too. Well, so the question was about the arguments and passing the arguments in, I believe, and so basically, you're the one defining the kernel. So if you have a global variable that's important to your calculation, you would add some value out here and then use it in your kernel computation. And then when you transferred that over, you would have to allocate something on the device and then transfer that data over for that kernel to be executed. It would be, you'd have to manage that the same way. That global variable would not automatically exist on the device. Think about the GPU as a clean slate. If you haven't transferred it over there, it doesn't know anything about it. So just to back up and recap, we've talked about a very simple example right now, just add vector, but only a vector of 1. But we've built it in a way that we should be able to make it work on a vector easily. So how do we run code in parallel on the device? And this is the dying question. The question you're all dying me to answer at this point is why would we have 1, 1 there in those brackets? And this is a nomenclature that NVIDIA came up when they did this. And so it's really a number of blocks and number of threads. And we'll explain that in a moment. But for this example, let's just talk about n, the first one. And so if we take add n and then give it these particular parameters, instead of adding that execute just once, it's going to add it n times, and all those are going to be in parallel. And you have very little control over any synchronization that's going on between those when you launch it in this way and run it. And I'll talk more about that. So if you want to do a vector addition as opposed to a scalar addition, each of these parallel invocations of add is referred to as a block. And they're block and threads, and we're going to start with blocks, okay? Then the kernel refers to the block's index with a loop, with a variable, block index x. Now, don't get hung up on this. This is just like a reserved word. It's something that when that kernel gets launched, CUDA says, here's what the block index x value is, and then you can take that and use it in your indexing. Each block has a value from A and B and storing the result in C. So this is what you would start looking at if you had 3 vectors, A and B as your input vectors, and C. You would go out and execute it with that n value. You'd launch it, the kernel launched with n, and then each one of these n kernels would compute on some data indexed by this block index that you see here. And we'll dive into that a little bit more. By using this block index x to index the arrays, each block handles a different index. Now, let's stop for a minute and think about that. You can roughly compare this kernel launch with n to a for loop that's computing across an array in this situation. And that's, in some ways, what it's doing. It's launching that kernel in multiple threads at the same time, but you don't have a loop in there, right? And if you were just having an OpenMP loop or something, that would be iterating over this vector and doing the addition and loads and stores for you. Here, CUDA is telling it what index it's going to work on, and then the kernel and core take that, compute it. We write this code like this. This is the kernel, and then when we run it in parallel, here's what it looks like. When the kernel launch happens, CUDA runtime looks at how much work it has, and then allocates that work. And then when the kernel runs, it says, oh, I'm block index.x, I'm 0. So I'm going to take that particular piece of memory, do the addition, and store the data back in C. And then same for the other blocks. And you could have 512 blocks, you could have 1,000 blocks, you could have a lot of different blocks there. And that's essentially the way that would happen. Now let's just take a quick look at main and try to understand how this new vector addition would change with those. So it would just be a simple extension of making it vectorizable. We started out looking at scalars. Here, we really have to go in and add the mallocs and initialize the data for the vectors instead of the scalars that we had. And we're going to do 512, and we have those same device copies. Remember, we still have pointers, and then we have host copies. And since we're switching to vectors, we changed those to pointers as well. And then we do the same. We're copying them, making the mem copy of A and B over. Then we're launching n times. In this case, it's 512. Goes out and fires those off. You're done. When it returns, you copy the data back. In addition on this, you have to free the host memory as well as the device memory. So the question was about the N1 notation. And so N is the number of blocks, and 1 is the number of threads per block. And there's some graphics. If you go back in history and look at even the OpenCL spec, they can have, one-dimensional blocks, two-dimensional blocks, three-dimensional blocks. And a lot of it has to do with image processing and graphics and how people were initially using these devices. So let's just do a quick review. The host is a CPU, the device is a GPU. You got to use this global keyword to declare a function to run on the device, and it's called from the host. And then you need to pass the parameters from the host into the device function, and those are pointers or to the device memory typically. You have some simple calls that mirror what you do on the host side, malloc, memcopy, and free. And then you can launch these parallel kernels pretty easily by just adding, changing this notation here. And then inside that kernel, you access different data by using the indices that CUDA runtime provides you as the kernel's being launched. If you look at the parallel threads, and this didn't come out too well, I'll walk you through this, but basically that block can be split into threads. This was the, if we wanted to use threads, there are, we're going to change the vector addition to use parallel threads instead of parallel blocks. And what you can't see here is, in here is the animation, because it's an animation. You're really going to use thread index instead of block index x. And so what does that mean? That means that CUDA gives you a reserved word, thread index.x, in addition to block index.x, that gives you information about what data you should be accessing in the data structures. The main will require a change as well. Now, if you look at this, it looks pretty similar to what we had before. You've got your allocations and initialization, and then you come down here, and now we want to change this, and basically this is n threads instead of n blocks, and what we do here is we make this a 1 and this an n, and again, that is hard to read right there, but just transpose the two values that we've talked about already. So you've got 1 block and n threads. And there are limits, and it depends on which GPU you're working on, about how many threads you can have per block and how many blocks you can have and those types of things. But I don't dive into those details too much because they are GPU specific. That's the only change. So in that case, basically, you're going to be executing that with threads instead. In a block sense, each block implicitly has 1 thread in it, and that 1 thread is executing within each block. So you already have that. The real question is now, how can we use both blocks and threads to have many blocks with many threads and have them all executing? And so Let's take a minute and think about the indexing. In the earlier example, when you're talking about a vector and a block or a thread, it's easy to index into your array. When you start combining blocks and threads, it gets a little bit more difficult. And so it's no longer simple just in terms of thread or block. Basically, you could think about one long array that we want to compute. And you could have a number of blocks, and each block has a number of threads. And then if it was just one-dimensional, you know, we could break it up this way. We'd have a number of blocks, 0, 1, 2, 3, and then each one of these thread indices would be in there. And it would be similar to how you lay out a multi-dimensional array in C, for example. What you need to do is go and use these reserved words to calculate where you are in that long array based on the values you get for block index and thread index. And what we're seeing here is a lot of times you'll see a CUDA program. The first thing it does is go in and calculate some kind of index based on these values and then use that index for the rest of the application. And that's the way, instead of using a loop to iterate over these, each kernel gets a different thread and block index, and then it executes just on those slices of data that it's been given access to. And the runtime provides those values. For every kernel that's run, these are different values. And at runtime understands the data layout of the data on the device, and then gives the kernels a starting point to go execute. And so just another example, if you had this long index and you had an element here you wanted to access, element 21 in just a regular C array, then you would have something that looked like this. You would have, say, your 8 threads per block. Then you would have, you'd be in the second block, and then you'd be in the 5th element, and your index would work out this way. And it's simple. It looks very similar to C arrays, and if you do multi-dimensional arrays in C, how you would just calculate those values. So it's not too complicated. It can get complicated, but for the examples we're looking at here, it's not too bad. Especially if you start doing the 2-dimensional and 3-dimensional things, it can get a little bit hairy. So that value M, remember here, is the width of the block, and we've used that right here. Well, CUDA runtime provides that value as well. So there's the blockdim.x that tells you how many threads you have per block. And then you just use that in your code, you calculate index, and so this is the one line we add to make it vector and using threads and blocks. And so that's the simple change for the vector addition kernel. Now, what changes do we have to make in main to do that? Again, it looks almost identical. This slide is identical to the earlier slide. The only thing that's changing is really this section. And this section's a little bit more complicated because they didn't use constants in here. They actually made it a little bit more easier to change with directives. They've got threads per block where that's some predefined value, let's say 512. And then you've got the number of size of the vector divided by the threads per block. And again, there's not code in here to make sure you're running over the end, and we're assuming it's round numbers and divides evenly and all of that. So this is really all you would need to be able to run that parallel thread block CUDA kernel. So basically, this was the question that I tried to answer earlier. Why do we even need threads? Why don't you just give me a bunch of blocks and I'll use those blocks? This is where it becomes tied to the GPU architecture somewhere. If you look carefully at the GPU architecture, each streaming multiprocessor has some number of cores, and then it has some shared memory with it. The shared memory is not infinite. In recent GPUs, that shared memory could be 16K, 32K. I mean, we're talking small. So it's very fast and very high bandwidth, but it's very precious, and you have to manage it carefully. And so what that parallel block does is gives you an opportunity to map your work to that particular core and manage that shared memory. And that shared memory, that block also allows you to communicate. Threads can communicate with each other, and they can synchronize with one another. Blocks can't do that. When you fire off many blocks, you can't be assured there's any order in the execution of them at all, and there aren't tools in the CUDA toolbox to allow you to synchronize. Now, you can do some things like use atomics to enforce some kind of ordering, but that would probably kill your performance, okay? So let's just take a look at how some of these things would work. So if you take something like the vector addition that we talked about earlier and just make it a dot product, really a dot product is, that first multiplication, but then you have this summation, and that summation is really like a reduction. And so you're taking all those values and adding them together. And so what you see here is just a schematic of how you would do that, and you could probably see how that would easily map out. You do some pairwise product. Each thread that's launched is going to do dot, and it's going to get the pointers to A vector, B vector, and C vector, and then, or C is a scalar there, and then each thread does a pairwise product. And so that's pretty easy. We can see how that part works. You're going to create a temp. Now, when you get to this final sum, it gets a bit harder because you want to take those values and add them together, but each value in a thread is really private. And so that temp that I've created there is not in shared memory, and it's not in global memory, and it's not in host memory. It's just in the local private memory. And so how do we add these things together? Well, that's where you can start sharing data, and that's where this idea of shared memory comes in. It's extremely fast, user-managed cache, basically. And you declare it with this shared keyword, CUDA keyword. It's not visible to threads in other blocks running in parallel. So this is where I go back to the shared memory. You have all these different blocks, and then the threads in this pool can all access the shared memory, but they cannot access the memory over here, and block 1 can't access that shared memory. So that's good because it kind of limits your scope. You have to think about where your data is and how much data you're using, and that is one of the reasons it's very fast. If you look at the multiplication and serial addition, there is a way to do it, and you could, inside the shared memory region, you could create a shared temps and then store your dot in a temp vector that we have local, but it's in shared memory. And then have one of your threads out of your 512 threads go through and add all of those up. And what you see here is thread 0 checks to see if it's thread 0, and if it is, then it goes through a for loop. And this is just a normal for loop, and you're accessing shared memory, and it sums all those up and then stores the reduction back in C, okay? We have this dot product, and if you remember, we were talking about, what was the benefit of having threads and blocks of threads, and it boiled down to this shared memory concept. You could have the kernel go through and do the summation of the individual private data, and here we've created the shared data. We've added the shared keyword to make it a temporary vector that each thread writes into its partial sum, and then we have that one thread go through. And even though you've got all these threads doing work, 512 of them perhaps, only one of them is doing anything interesting. And so, this is just for an example. You could do things like reduction trees and things like that using this, and that's what some of the other examples show in the slides. So this is summing things up. Now, it does have a problem, and that's where I want to introduce some other concepts. So in this part, we performed a parallel pairwise multiplication. The shared memory stores each thread's result. So now all the threads in that block can see all of those temporaries. We sum these pairwise products from a single thread. And then it sounds good, but we made a huge mistake, right? And so this gets back to your caveats of parallel programming. So if you look at this, in parallel, each thread writes a pairwise product into this temp vector. And this temp vector is shared, so each thread computes and then writes, and then you sum them up. But there's an assumption here, and that assumption is that all of the threads have written their data in that value before you start reading it. Because if you look at this, say block 1, and remember you have no guarantees of any block ordering here, so just because 0 is before 1 in a numerical sense doesn't mean it gets scheduled first. It might get scheduled last. And so when you look at this, one of the things you have to worry about is the thread finish writing in step 1, not I'm sorry, the thread 0 finishes its write step before everyone else, and then when it goes in to start doing the sum, it actually uses old trash data and does your summation that way. And that's what happens here, and then the write from the next block comes in. I'm sorry, the next set of threads comes in. And so that, that is something you have to think about, and it's easy to fix in this example. You've got the thread barrier, and so what that's called in NVIDIA speak is sync threads, and basically we're going to do the same thing we did before. We're going to have everybody compute their product, store it in the shared memory temp, but we're going to make everyone stall at this point before they can proceed, before we actually sum up those pairwise products. And if you look at it, the execution would look something like this. You'd have your threads executing, and then they get to this point, and when they hit sync threads, they would stop, and then only the threads within that block are synchronized. So sync threads is all threads, it's not all blocks. So remember, there's not really any way to coordinate between blocks. You don't know what the order of evaluation is for those blocks. So the sync threads scope is just for the block, and so the thread's in a block. And so if you go back and look at it, it looks like this. And then once you pass through this, you're assured all of the threads that are executing this particular function have made it to that point within that block, and then you do the summation. If we go back and look at main, we've changed not much, just the size of C, because we're doing a reduction now, and that reduction is returning just an int rather than a vector events. And same here. In this dot, we're just executing on, for examples, one block and n threads. So we're having those n threads compute. Then we copy the result back, which again is not a vector, it's just a size of int, and we're copying that from the device back to the host. So just a review, we're launching the kernels. We talked about how to launch the kernels. We created the add function, and you can launch parallel threads with this type of nomenclature where you've got number of blocks, number of threads per block. Then we use this thread index to access the threads index inside that block. That typically has to be combined with the block information you get from the runtime to be able to access the data in global memory that you want to access. And that's what they're saying here, and then you've got these values to help you do that indexing. Shared memory was introduced, and this data, remember, is just shared among threads in a block. And remember, there's the global memory. Now, the global memory is really the memory that is on par with the host memory. Global memory is on the order of gigabytes, and the Fermis that we have, it's 6 gigabytes of memory. And that memory is available to all the cores, but it's very slow. And so what people do is stage that data from global memory down into shared memory, and then compute on it there, and then when they have results, write it back to that global memory. The global memory is much larger, but it is performance-wise much slower than shared memory. Then you look at the sync threads as a barrier. This is just a way. It's a normal barrier. The only thing you really have to remember is its scope is limited to block. And this has to be used to prevent the hazards. And you guys probably have seen many of the hazards, so we're not going to go through all of those. But now let's think about multi-block. We've talked about how to synchronize the threads and start gathering up the summations across one block. And remember, that's pretty easy because we have all the threads, we can synchronize the threads, and then we can have some shared memory. We can store that data in one variable and then write it back out to the host. But one block's not going to do much for you. I mean, these GPUs can have dozens or hundreds of blocks, and so you want to make as many blocks as your problem can handle. So let's switch and look at a multi-block version of the dot product. So the multi-block version would look something like this. Very similar to what we've done already. Each block computes a sum of its pairwise products like before, but you have multiple blocks. But this array, see, index down here is 512, it's 0, 512, and then you'd be down at 2048, and different blocks would be starting at different positions. That's really dictated by the runtime. The runtime is launched on a certain grid, and it has access into this array, and using the indexing that I showed you earlier. You index into that with your kernel. Then if you look at this, you have the summation that we talked about, but that's really just a block summation. What you really want to do then is take those sum values that you have and sum them together and store them in C, which is the final result for the whole dot product. If you look at this, basically this is the kernel. If you look at it, there's potential for a race condition here, because basically what you would do, and again I apologize that that's overwritten because of an animation, but basically what you would do is after you summed up your values in your threads, you could just write it back to global memory, and you would say, okay, I want to add to C the sum of my local threads because I'm thread 0 and I'm speaking for all the threads in my block, write it back. And so you could do that, but this is where the unforeseen race condition raises its head, where you get all these potential memory consistency and race conditions, and that's where you can use some of the atomic operations. Now, atomic operations, just like on a CPU, are really valuable because they let you do things that you can't do any other way. All kinds of semaphores and mailboxes and other types of handoffs. But they're very expensive, and so you wouldn't want to do, for example, the sum by just having all of the threads do an atomic operation, because it would essentially serialize all of your atomic operations, all your threads on that one atomic operation. And so basically a race condition occurs when program behavior depends on the timing of two event sequences. And what happens, and why this is, needs an atomic, is the way this would work is you'd read a value address at C from global, you'd add the sum to the value, and then write the result back. And that's a read, modify, write that's pretty common. If two threads are doing this at the same time, you know, these sequence of events can be interleaved in different ways. And if you look at that, here's one way that sequencing of memory operations could play out. And you get a 7, which in this one looks to be correct. But you could also get this type of ordering. And this is where you'd have a race condition, because both the threads read 0, and then they did some computation, but they were essentially hitting a hazard there of reading the value and not having them sequentialize like they should be. And so that's an incorrect answer, and that's where you can use atomics to get around this problem. Now, CUDA has these atomics. Again, they're a pretty rich set. You can do things like compare and swap and exchange, increment and decrement, addition, min and max. Those are all common. You see those in MPI and other programming models as well. But it gives you that predictable result when you access memory. And so basically in this example, we're going to add that sum up from all the different blocks using an atomic operation, the atomic add, and that's what we do here instead of doing that, just that straight write back to memory. And so that, you know, is a, you know, we went through this, we'll review it again in a minute, but that essentially gives you your multi-block dot product. Here's the main main kernel again. A few changes. We've added this in to make it multi-block. You still have a number of threads per block you're going to allocate, and then you have a number of blocks. And again, depending on your computation, one of the tricks is getting that balance right. And I'll show you an example in a moment where that might, you might actually have to do some sort of auto-tuning. And for each GPU, it might be a little bit different, and you need to go in and tweak it. So we've talked about race conditions. We've talked about atomic operations. And that really is the quick intro to CUDA. Now, I'm going to switch gears back to a more complex example, and I'd be happy to take any questions. I answered several questions over the break. Is there any more Are there any more questions on just basic CUDA? I mean, there's a lot more to it, but this is a starting point. Okay, so that's fine and good. We've talked a little bit about dot product and a couple of the other quick examples. What I want to think about now is just a computation that's pretty familiar to everyone. It's n-body. N-body algorithms are popular, even if you look at Gordon Bell Prizes and some of the other things that have been defined and awarded over the supercomputing the past few years. N-body is still alive and well. There are a lot of different algorithms to use for n-body. For this example, because we want to keep it concise, we're just going to talk about the all pairs interaction problem, and just to give you an idea of how you would do it, thinking about a GPU. And there's a lot of other algorithms out there, FMM and long-range force approximations and Barnes-Hut and other things. People have done those on a GPU too, and you can certainly find out more about those in the literature. So just thinking about the basic problem, we've got position, velocity, mass, and perhaps some other attributes based on what type of simulation you're doing. The big key here is you have to do these summations, and these summations for the force are across all the particles that are your neighbor, and in this case you're considering all of them because you're not using any type of cutoff distance. And then you have to do exponentiation and a few other things to actually do that. Now when you think about that, I mean, one thing you could do is just put all the particles in global memory and have the threads access those particles to do something like this summation that we're talking about here for each particle and each force. There are a lot of different ways to do it, but one of the ways that was proposed in GPU Gems, and I'd refer you to that book if you want to see a lot of interesting examples of the way people have tried these problems, is to think about this all pairs calculation as a force matrix. And what that means is, if you did it on a CPU, you could easily write a for loop, nested for loop that goes out and just sweeps across the array each time and sums up the forces on each of the components. There's another way to calculate the total forces, and it's by creating a force matrix. And I'll show you a picture of that in a moment. The nice thing about it is it gives you a lot of parallelism, but it really requires a lot of memory. And that's one of the things you need to think about, because what you're going to be doing is staging some of these particles into shared memory, computing with those, moving more particles in and computing with those, and keeping a sum as you move across the set of particles you have to deal with. And so if we just look at this strategy, I mean, what I mentioned earlier was a reasonable way to do it, but essentially what you have to do is start thinking about tiling, because what you want to do is move the data into shared memory. You can move as much as you can get into that shared memory, but remember that's only 16, 32, 48K, so it may not be very much. So we're going to break these force matrix up into a square region of the grid that has P rows and P columns, where P is the number of particles that you're considering. And then in parallel, what you're going to do is you're going to evaluate each one of those particles sequentially and calculate the force on them. And then you're going to have be staging in the particles that you're computing against. And so I'll show you code for this in a moment. The key is that you've got a lot of parallelism here, and this could be some combination of blocks and threads per block, so you could literally have thousands of these being executed, and then as they sweep across this grid, they're pulling in the body descriptions into shared memory, computing that segment, and then moving on. And so if you look at this body-body force calculation, and this is the most basic calculation that you need to do, it would be here, notice it's device and not global, and the reason for that is it's being called by another CUDA kernel that's already executing on the GPU. So you give it device, and then body-body interaction is going to get some parameters, and these parameters, since it's already on the device, you can use the float 4 value. CUDA understands what those are. And then you basically do this computation. And And what you're doing here, and there's more to it, but we'll pop up in a second and I'll show you what the harness code for this looks like. But at the lowest level, this is what you're calculating. You're calculating the distances, the square, let's see, some other things there, the cube of that, and then doing some square roots and inverses. And then basically updating your velocities with that. And that's just the body-body interaction. And remember, that's only about 21 flops or 24, right? We could count them up, but it's not very many, and it depends on how you use square roots and inverses in that calculation. That's really the kernel of your computation. But when you're evaluating that tile, as I said, what you're going to be doing is pulling data in to the shared memory. Each thread's going to be executing this particular routine right here, and that's the tile calculation. The shared position is an array in the shared memory, and if you look at that, what you see here is you've got your tile calculation, and then you've got extern shared float shared position, and then what you're going to do is for some number of iterations in your particular block, you're going to calculate the value from your current position against the data that's been staged in shared memory. And this position describes the particle that you're currently evaluating. And you do this multiple times because you're working across this grid with tiles. And then you are calculating acceleration and returning that as a float 3. And remember, that's float 3, so that's exactly the way it sounds when you're on the GPU, because we've been doing graphics and things all these times. They have float 3 that's just or float 4 that's just a short vector of floats. And that's a type. And so you get that for free and basically pass those around as parameters and return values and such. And then so just thinking about that, you've got these tiles to size so that they basically bring in as much data as they can into shared memory. And then remember, they've got already a particle that they're computing on, and they're going to be working their way across here, calculating the sum of forces on that particular particle for all the other particles. And as you hit these synchronization points, which can be variable based on what number of which GPU you're using and how much shared memory you have, they'll be staging data into this memory and then compute for a while, and then synchronize, and then load some new data in and continue. And your parallelism is here, and you're computing sequentially across each one of those rows. And again, this is something that the right exact number is something you just have to determine with the GPU that we were looking at, and then you'd have to balance that against how much register and shared memory space you have. Okay? And then if you look at the thread block execution itself, if you look, and that is all the threads in a particular block working across there, it would look like this. Calculate forces, and that's a global, so that's getting called from the host, and you get some pointers into the memory that you've already allocated. Then you've got the shared memory that's an extern that I'll show you in a moment. And then you basically pick a particle that's your position and start the summation of the acceleration, initialize it, and then do some indexing into those values. Get a global x, okay, that's my position, that's who this particular thread's going to represent right there. And then basically you're going to start working this tile across, and each thread in there in your block is going to pull some data in, and so that's what's happening right here. You're loading a particular set of values into that shared block position. You're calculating, and then, you're synchronizing, then you're doing your tile calculation, and then you're synchronizing again because you are immediately coming around and starting to update that value. And so that's the way you would work across there. And see your index variables I and tile are the values that you're computing as you move across that particular row for each one of the threads and blocks. And then here, you're going to save the result in global memory, and that's basically the result that you get from has been accumulated as you execute tile calculation. And then you save that back into the global array. And that's your acceleration. So, you know, there's not a lot of code here, but it can be intricate. So you've got to think about what you're going to stage into that shared memory to use, because it is much faster than global memory. This is what a set of threads and blocks would look like to calculate all those forces. You would have n bodies, remember, and then you'd have some number of threads and then some number of blocks, and those would be able to progress at different rates, because each block would be able to progress at a different rate because it would be loading shared memory. So all the threads would have to stay somewhat synchronized within that block, and they would have to be synchronized on these boundaries. But the different blocks could be executing at different rates because there's really no synchronization between those blocks. And the only thing that happens is when you're updating the memory and locally, and then actually storing that result back into the global array. So the performance effects, there was a question earlier about block size and how that affects things. And if you got a bigger block, you'd have fewer threads, but you know, it depends on how much memory you're using. These are some old performance results, but they are from that particular article. And it gives you an idea of the kinds of rates you can get. There's gigaflops. This is on an older GPU, but you can see just keep increasing the number of particles you're considering. You see the floating point rate go up quite high for that GPU. I think it was a G80. And then here is the trade-off. And almost everyone who writes an application for a GPU goes through this exercise of trading off the threads and the blocks. And it's a pretty easy parameter to tweak. And this just gives you the idea that in this case, the block size, as the block size increases, you see the performance increase too, except when you've got a very small n, because each block doesn't have enough work. So just, you know, that was a very brief example of kind of the trade-offs of writing a kernel to do n bodies. There are a lot of other ways to do it, and you know, one of the ways was to create this force matrix, and the force matrix stages that data into shared memory and sweeps across there, and you get data reuse out of that because each thread doesn't have to load the data value from global memory. It has to load the value into shared memory, and then all the threads make use of that same shared memory item p times for that particular block. And so you get data reuse that way, and that's an improvement. So there are a lot of examples out there. I would encourage you to go look at the Shock Benchmark suite. There's CUDA, there's OpenCL, there's some other examples out there. And you know, of course, the NVIDIA site has a lot of CUDA examples. That gives you a sense of what you need to think about at the coarse granularity for programming a heterogeneous system like an NVIDIA GPU. Basically, that you have, like in OpenCL and CUDA, the ability to do a two-dimensional or three-dimensional work structure. And these blocks work very similar to what I've showed here, because the kernels get fired off on the blocks in those grids, and in a way that that block index now has a Y component and possibly a Z component to them, and you have to index into that block using those additional parameters. So if you have a big array, you can actually do the type of calculation that I showed here, but you have to do it in an X and a Y and potentially a Z to do that indexing. It's a bit more complicated, but I don't have time to get into an example like that here. But it is very convenient if you have a problem that maps well to that. And we have a couple of those. We have a combustion code that's a large structured grid, and we've been able to take that and use these types of 2D and 3D features to do the computation on them, because they're just big structured grids, and you can easily map that into a GPU using that. And then the runtime gets a lot more say in what's going on there too, in scheduling and mapping the data to the threads. But that's a good question. I'd encourage you dig in a little bit and try it out. I've got about 10 minutes left, so I'm going to briefly go through a couple other things here with OpenCL. The reason I want to leave you with this is that OpenCL was a standard that came out about 4 years ago, if I remember properly, and it was an open standard in the sense that it would be a specification that people would get together and ratify, and then different companies would adhere to that specification. And if I had an OpenCL program that ran on an IBM system, I could run it on an ARM system and know that it would compile and at least run there. Now, you still might have the performance portability problem, but that's something you might be able to solve with some sort of auto-tuning or something like that. OpenCL looks an awful lot like CUDA. It's not quite as clever in the language constructs, but when you think about the concepts, I think you'll see them very similar. Really, the basic differences is in this terminology, the syntax, the API calls, and the compilation. And what I mean by that is, in CUDA, your compiler builds the kernels when you compile it. So you basically run that NVCC, and then it creates these CUDA compiles and creates a fat binary that has those kernels stored in that binary. In OpenCL, you can build them statically, but you also have this call that you can make to compile a kernel at runtime. So if there's, you could think about just-in-time code generation here for a specific device or for specializing a particular kernel, and you could do that easily. There's the language extensions. There's really an API in OpenCL, and then the kernels themselves have a compiler, but you don't see that. The kernels that you create in OpenCL are really like a long string, for lack of a better word, that you take and then you run the compiler on them at runtime, and they create that executable. They have other differences like buffer offsets and pointer traversal, but some of those are, especially when you're doing things like multidimensional arrays over the break. Somebody mentioned multidimensional arrays, and so you have to be careful with those things when you look at these pointer arithmetic, and be sure not to share data in pointers between the host and the device memory. Here's some other terminology you got to be aware of in OpenCL, but see, there's a lot of consistency here. In CUDA, there's a thread. In OpenCL, they're called a work item. In CUDA, it's a thread block. In OpenCL, it's a work group. Global memory, constant memory, shared memory, local memory, private memory. Wait a minute. You lost me here. So this is the one bad mapping that you need to keep aware of. In OpenCL, the thing that's called local memory is really called shared memory in CUDA, and then private memory is called local memory. And so when you're making that translation, just remember to keep that in mind, because that is the most confusing part of the transition. Now, they're very similar, and you have even tools that people have developed that allow you to take an CUDA program and start generating an OpenCL program from that, because CUDA has a little bit more detail in it, and you can easily see how you could translate most constructs directly to OpenCL. And so there's actually some research projects out there that have developed those types of tools. Function qualifiers, in OpenCL, it's underscore kernel, which, these make sense. The CUDA ones have historic meaning, but they're sometimes confusing. And then the variable qualifiers here, you've got what I mentioned earlier, device memory, global memory, shared, local, what I've already mentioned. And then here you have the example API calls and some of the things that you need to do. CUDA memory copy is in Q read buffer and Q write buffer. You still have to allocate memory. So there's a lot of similarities in there. If you know CUDA reasonably well, in a couple days you can pick up OpenCL. It's that reasonable. Things like kernel invocations change a little bit, and you have to compile the OpenCL in the executable. here's a simple example of the of how this works, and the difference for vector add, what we were talking about. See, there's just really some syntactic difference. One of the big differences, and it's a welcome one, is this indexing feature that OpenCL has. It actually has a get global ID, and instead of you having to do this index calculation manually here, it's got a global ID and a local ID that you can actually just ask the runtime for, and that prevents you from making more mistakes and having to have that line at the beginning of every kernel you write. And then the host code example, this is where it gets a little bit ugly. OpenCL has C++ version that's on the radar screen. And because of the language features in C++, like destructors and constructors and things like that, you can get rid of a lot of this, and that's coming. But right now, it's quite verbose compared to CUDA. In CUDA, this is what you would do to basically run a function. In OpenCL, you've got to create the kernel, compile it, set the arguments for it, create the range, and then go execute it. And that's a lot of overhead. But C++ version of OpenCL is going to hopefully fix that. I've stuck these in here, just open CL pointers for other things, and there were a couple of the tools that people have created. So I have a bunch of slides in here about advanced optimization topics, and those include things like NUMA effects and some of the things like memory coalescing and things like that. I'm going to pause at this point and answer any questions you might have, and then turn it over to Bronson. And based on how much time we have left at the end of the day, I might come back and do some of these. But I'm going to wrap up now. If there are any open questions, I could try to answer those. The question was about PyOpenCL, and I think one of the things that would be nice is a scripting language on top of OpenCL. So I think that's a great idea, because if you look at a lot of these GPU codes, the way they use the GPU is they have some harness structure, and then they predominantly try to offload all of their computation to the GPU anyway. So whether it's in Python or C or C++, it probably doesn't make a lot of difference, because most of the time you keep all of your heavy computation on the GPU anyway.